Hello everybody. I'm here with an example, a very simple example of the buckling, and I want to start actually with just a quick review of the equation. If you guys recall on the previous video, I did derive the equation for which will give us the critical load for a bar that is pinned at both ends. Now by pin, again, I mean that the deflection is going to be 0 here at one end and deflection is 0 also at the other end. And we use this actually as boundary conditions to come up with this. So again, it's confined in such a way that this is allowed to be compressed due to this axially compressive load. And the deflection is 0, but the slope is not 0. You see, that's the difference between a cantilever beam and a roller supported or pin supported beam. So slopes are not 0, as you could see, but the cantilever is a different story, and we'll talk about that later on in another video. By the way, we talked about the equation that gives us the critical load as being n squared pi squared EI over L squared, right? And the smallest load is when n is equal to 1. So if you set n equal 1, you end up getting this equation. This is, by the way, known as the Euler equation. So Euler has so many equations, so many formulas, and this is one of them. Now, one thing I forgot to mention in the other video when we did the derivation for this, using the differential equation and solving the differential equation and eventually finding this critical load, was that because we want to find the smallest critical load, we have to use the smallest I actually. If you have an unsymmetric cross section, meaning by unsymmetric I mean with respect to horizontal or vertical axis, the axis of bending. If I is different, you have to pick the smallest one, and I want to use this example below to illustrate that. So suppose we have a beam that is, or a bar that is pinned at both ends, or we have the confinement as you can see here in this picture. Let's say the length is 10 feet. Now, one thing to remember, guys, is that if you have something in feet, immediately change it to inches. It's a good idea to do that. All right, let's say this is an A36 structural steel with modulus of elasticity of 29 million psi, and it has a cross section as shown here. It's a 4x6 rectangular cross section. So this is what I was saying. The moment of inertia with respect to x-axis is going to be 112 bh cube 46 cube, which would be 72 inches to the power 4. But look at the moment of inertia with respect to y-axis. It's going to be 112 6/4 cube. You have to switch b and h. So this one is 32. So you have to use in this equation I sub y, the smallest, because that's the weaker section. If the buckling is going to happen, it's going to happen with respect to the y-axis rather than x-axis. So kind of like bending. How would it bend? In this case, for example, this is coming out of the, so if this is the cross section of this beam, the 4x6, right? And the buckling is going to happen about this axis. It's going to come out of the board or this tablet or your screen kind of. So that's how it's going to buckle, not the way it's shown here. But anyways, so let's go ahead and plug in. So formula is right here, pi squared. E is modulus of elasticity. I is 32. If you carry out the unit, guys, the unit should work out and the critical load should come out to be in pound. Okay, so this is the mistake, typical mistake. If you don't change this to inch, sometimes you might do this 12 times 10, and then you may forget to square, both of them. So you might say 12 10 squared. Not a good idea. So change it right from the beginning to inches. Okay? So 120 inches. This comes out to be about 636,000 roughly. So 636 kip. Okay? But now, this is the load needed smallest load needed to buckle a beam with the given properties, with this cross section and this modulus of elasticity and this length. But what if the before the bar or the beam buckled, it would be yielding? So let's go ahead and find the stress developed. So take the critical load and divide it by area. Area of this guy is 6 by 4. That's 24 inches squared. This comes out to be 26.5 KSI. So we say since 26.5 KSI is larger than what, or smaller than, rather what? Remember the yield for A36 is what? 36 KSI, right? That's what 36 is. So since this is a smaller, so obviously yield is not going to happen. Buckling will happen first. Therefore, the critical load would be 636 K. Okay, I will come back shortly with more examples of what happens if the end supports are different. So what if it's not pinned? What if it's a kind of cantilever type of support, at both ends, or one end is cantilever, the other end is free, and so on. So there are actually 4 cases that we're going to look at, and I'll come up with that in a few minutes of my time. As always, thanks for watching and listening.